Hey gang, and welcome back for another video here on jOeCHEM. Okay gang, this is going to be the worksheet solutions walkthrough for the worksheet, Ester Enolates Reactions, Concepts, and Synthesis Practice. Okay, so we've done a lot of chemistry dealing with, esters and more specifically ester enolates and all the wonderful things you can do like Claisen condensations, Dieckmann condensations, and all that great jazz. So we're going to just dive through the worksheet. If you're here, that's okay. You've seen the answers. Hopefully the solutions gave you enough background, but we're looking for the deeper dive. So without further ado, let's jump in. Okay gang, to start this worksheet off in problem 1, we have A, B, and C. And because I'm limited on real estate, we have problems A and B here. And what we have going on in both A and B is we're going to rank these acids from weakest to strongest, giving 1 to the weakest acid and 4 to the strongest acid. So looking at part A of problem 1, you can see we're trying to find, the strongest acid, and there's no kind of hydrogens highlighted or protons highlighted or anything like that. We just have the structures given here. But I think the thing you can kind of identify here is that in each structure, we have, carbonyls all over the place. And we spent a lot of time, during the instructional videos highlighting that when you have a dicarbonyl of some sort, if you have an alpha carbon wedged in between two carbonyls like this, one thing that happens when you have a proton fall off is the resulting lone pair that will end up right here is resonance stabilized in either direction, carbonyl wise. But remember, we learned with, dealing with all these ester enolates or esters that when you have an ester, it kind of makes this carbonyl carbon a little less partially positive. So the resonance effect isn't so great. So let's take a look. If we take a look at the structures right here, you can see the answers are already in red. So if we take a look here, you can see this structure is labeled as the weakest acid, and here's why. Yes, we have two carbonyls, but you can see that there's actually no dicarbonyl in this structure, right? A dicarbonyl is one such that you have an alpha carbon wedged in between two carbonyls, and we actually don't have either of these carbons having a carbonyl on either side of it. As a result, we kind of only have carbonyls right here that are alpha, only to one carbonyl. So the acidic effect isn't as great as a situation like this carbon over here or this carbon over here, which is in fact wedged in between, two carbonyls, aka dicarbonyl. So this structure right here is a very easy one to say that we have just, this is the weakest kind of acid here because there's no kind of that wonderful dicarbonyl effect. Now, the one thing where we kind of have to split hairs is between these two structures right here. And hopefully, based on that little kind of bioblast review that we just did over here a second ago, you can see that this is just a pure 1,3 dicarbonyl. If there was a lone pair right here, we can see that there's great resonance both here and here in either direction. There's no kind of resonance group over, or oxygen or anything like that to kind of, dampen how partially positive either of these carbonyl carbons are. So we're looking pretty. Now, the one difference over here is if we have this situation going on, yes, we still have the same resonance, but I think what you can see is it's this oxygen over here that lends electron density through resonance this way that kind of makes this partial positive on this carbonyl a little bit less. As a result, this acid is weaker than this because the resulting positive, negative charge isn't as comfy as it would be right here. That's why we get weakest over here, no dicarbonyl. Second here because of the ester making this carbonyl carbon a little less partially positive, and our best situation right here. Moving on to B, right? We can see the answers in red down here. Again, we're going, acid ranking from weakest to strongest. Now, you can see we have a whole bunch of dicarbonyls right here. This one is easy to point out as the weakest because we only have a singular carbonyl. That means the resonance that we get if we had a charge either on this alpha carbon or this alpha carbon, we just have less resonance, number one. Now, we have to kind of compare the quality of these dicarbonyl situations over here. based on our discussion up here, I think what you can see is right here we have a diester. And because of these ester groups right here, they're the ether parts of your ester, the partial positive nature of these carbonyl carbons are a little bit smaller than what we have over here. I'm drawing those partial positives to scale because these oxygens kind of lend electron density to our carbonyl carbons via resonance like this. So this gives us our second most acidic structure. This gives us our third most acidic, and we get our fourth most here because this is just your plain old, we just have ketones here, 1,3-dicarbonyl. Strongest acid here, second strongest acid, third strongest, dead last, obviously going 1, 2, 3, 4. Okay, gang, let me wipe this up and we'll finish off problem 1 with part C. Okay, gang, let's finish out problem 1. So if we take a look here, what I gave you in problem 1 were 3 reactions, completely filled out, but what was up to you was to actually identify, did this happen or did this not happen, right? Was there something problematic with the reaction such that it wouldn't occur as it was drawn, or was it good to go? So if we take a look here, we see we have 1 no reaction and 2 reactions were good to go. And let's explain, why or why not these actually occurred. In this first problem, what you can see, right, we have this ester. We can see in step 1, we have, sodium methoxide and methanol, which matches kind of the ether part of our ester over here, and then just some acidic workup. And then if we kind of look over here, we kind of see the ester represented twice. This, the way it kind of came in over here, but over here itself, but minus this little ether part. So this looks like a Claisen condensation, but does it happen? And in fact, this one does not occur. And here's the reason why. If you can kind of see up here, the very last step of a Claisen, as we've talked about, is when you knock off the one ester that gets attacked, when you knock off its kind of like, ether component and the ester as a leaving group, there needs to be this final acid-based reaction because this is not a quality leaving group. But we get around that by the minute it gets kicked off, it comes back and it deprotonates this very acidic dicarbonyl, this carbon wedged in between 2 carbonyls. However, you can see based on this alpha carbon being tertiary at this point in time, once the Claisen happens, this carbon is now quaternary. There's no hydrogen, there's no proton left over to grab, which is why I kind of drew this up here. This methoxide is going to come back and hope to find a proton here to abstract. Doesn't exist. So as a result, if you can't satisfy that criterion, Claisen condensation does not happen. So that's why this was a big old X no reaction here. Moving on to the second one, what we see is, again, we have another ester. And in the first step, we see kind of the corresponding, we have sodium ethoxide, ethanol matches this little piece over here. So we're not going to be doing any, transesterification. So all that happens in the first step is we deprotonate this position. And just to save some space, all we basically get is a nucleophile right over here on the alpha. We get an ester enolate. And then in the second step, no Claisen condensation here, just a good old haloalkane primary carbon right here. We have a good nucleophile. We're just doing some SN2 right here. And you can see the SN2 product over here. These 2 groups are kind of the groups we see over here. And we see this carbon, which is this carbon, now attached to, I'll asterisk this. Nothing wrong here. That's a good reaction. And then finally down here, last but not least, you can see we kind of have, this component is represented right here. That's our kind of base that will make this our ester enolate right here by deprotonating. And then we just have acidic workup. So this is just another Claisen condensation, right? And when you look at the carbon right here, the connection point after the fact, that's tertiary, which means there would have been a leftover hydrogen when the leaving group got kicked off to come back and grab. Claisen condensation would go through. This is a thumbs up. So that does it for problem number 1, but we got more work to do. I'm going to clean this up and we'll tackle problem 2. Okay, gang, moving on into problem 2, we have 7 kind of complete the reaction type questions. So here are the first 4 of them. So if we take a look at this top one, right, we obviously see the answer in red, but let's dive into what happened here. So we see we have kind of a 1,3-dicarbonyl situation, one of them being an ester, and we have a first step of NaOH and H2O, and then a second step of H3O plus and heat. Now when you see this combination, it's almost a dead giveaway that it's going to be a decarboxylation type problem. Sometimes these are hard to recognize if someone is being a bit mean and they write your ester like this, kind of hide it from you. But in this case, the ester is drawn out for us because I'm not trying to be a big old meanie. So if we have this, what the first step is going to do is that we're just going to hydrolyze this ester. We're going to revert it back to a carbonyl or a carboxylic acid state, and we'll kind of do this. I'll write this in blue to make sure you know it's kind of like a step here. We get a carboxylic acid, and then what we're going to do from here is we actually pump in, acid and heat, and what that does is facilitate the decarboxylation. To draw the arrows for you really quickly, if you're interested or into that, what we kind of got going on is there's kind of a coordination between the carbonyl oxygen a few positions away and the hydrogen in the carboxylic acid. And when you've got going on is this carbonyl reaches out, grabs that proton, that frees up these electrons right here to swing down here and form another double bond to carbon right here. This kind of forms your CO2. And at that point, you don't need this bond anymore. So it actually kind of swings on over and completes the circle to account for the bond that this carbon lost when this oxygen took it to grab the proton. So at that point, you kind of get like a little intermediate that looks like this. You get an enol type intermediate, and that immediately flips back to its ketone counterpart with the acid that is present. So what you can kind of do is just use more hydronium or whatever acid you have. This, whoops, I lied to you. We actually have water kind of do some cleanup for us. Goodness gracious, I'm a mess. We have water come on by. Water grabs this. Oh my gosh, I'm so sorry. I'm all over the place. We protonate our double bond, and at the same time, water performs a deprotonation, double bond forms. We flip back, right? Keto-enol tautomerism. A little rusty, sorry about that. And we get to our product here where you essentially just wipe that whole group away, which started out as an ester and just goes away and is represented as CO2 that's given off into the air. Okay, moving on to the second problem. We have these 4 steps here. I know it's a bit crowded, so I apologize for that. But I liked this problem because when I came up with it, I wanted to pull back some of the older knowledge, tie in some older knowledge that we have. So we just have a regular old ketone here. But in this first step, you might remember this from some of our carbonyl, ketone aldehyde type chemistry days. And what this is really going to do is a Baeyer-Villiger oxidation. So we're going to take our carbonyl and create an ester out of it. Now remember, one thing we have to remember here is how migratory aptitude works. We're going to insert an oxygen to the left of this carbonyl carbon, but where that happens is going to, the side is going to be determined by which one is more substituted. So because we have secondary over here and tertiary over here, we're going to insert an oxygen right here where this carbon is and slide everything down. So that's, in my mind, the key to this problem. The very first step, you end up with this. You insert an oxygen right here, and then this next line is actually this tertiary carbon right here. So you just kind of draw this. I like this problem because of the fact that it pulls on some knowledge. We have a reaction to make esters, and one that starts off from a ketone or an aldehyde. And then from there, 2 through 4, we just have a Claisen condensation. So step 2, we'll make our ester enolate. Where we're going to do that is on this side because our ester's over here. So after step 2, we have something like this. And then you can see we bring in another ester in step 3. So we're going to attack from this position right here. So that's why in the problem, you see this part of our ester represented right over here. It's this carbon right here that is this carbon over here, dotted in blue, dotted in red, dotted in blue. And then you can see the connection point is this, not the connection point, but this carbon is that carbon. And then 4 is just that cleanup step. So just another Claisen condensation. Now in this middle problem right here, I'm going to switch over here. I like this problem because what I wanted to do is give you the product and have you come up with the reactant. And I say reactant singular because it's only one. If you notice over here, we have there's obviously a cyclohexane involved. And you can see that we have sodium ethoxide and ethanol. And then what we have over here, right, we see ethyl group over here. So I could replace this over here as ET. And then we obviously have some tie-in with the ring. We know that it's this carbon that's going to be the connection point between this side and this side. But obviously this side down here connects over here. So if you draw this little squiggly between the 1,3-dicarbonyl that we have at the end, right here will be the connection point, because remember, our ester enolate will at least have one carbon alpha over here. That's a part of it over on this side. And then what I did was I numbered 1, 2, 3, 4, 5, 6. So since this is a Decarboxylation condensation, right, I kind of started by doing 1, 2, I drew these positions up to here and I started numbering 1. And then I did 2, 3, 4, 5, 6, 2, 3, 4, 5, 6. And then it's at this position right here that used to be an ester, but it lost its kind of ether component, and that ether component would match not only what did the deprotonation to kind of create our ester enolate, but also on this side of the Decarboxylation product. And that's why I tacked on the O, the oxygen, and then, on the solution it's written like this. But these are equivalent. Okay? So a little Decarboxylation problem where you came up with the beginning and I gave you the end. And then last but not least, we have, for the first part of problem 2, we have a bit of a long, what is actually a melonic ester synthesis. And hopefully, I know the mechanism is really long and tedious, but it's really just a couple of ester enolate SN2 reactions followed by a decarboxylation at the end. So if you take a look here, our first step here is we add in our corresponding base to what we see as part of a component of our ester. So really we just have an ester enolate right here. And then we toss in ethyl bromide. So really after the first 2 steps, we just have this. Just 2 carbons off of our initial product. And then we do it again. So now we have this. And then again, we throw in another group that is primed for SN2 attack. So then we have this. Oh boy. Right, 1 carbon, and then the ring. And then we do a whole bunch of work, which mechanistically sucks to show, but we really just kind of wipe these esters away. We make them carboxylic acids, and then one of them goes away through decarboxylation, which is why you see this carbon stick around right here. That's why then one of these is completely gone. One of these turned into the carboxylic acid, and then we have our ethyl group, which is right here, and then our singular carbon attached to benzene down there, and that's your melonic ester synthesis product in a complete the reaction type setting. Whew! All right. I know there's a lot going on here, but if you can do these, I'm pretty confident you can handle anything your professor or teacher could throw at you. But we're not quite done with problem 2. We have 3 more. Let's finish it out. Okay, gang, to finish out problem 2, we have 3 more problems, so let's just rip right through them. Okay, so in this first problem right up top, what I asked you, I gave you the beginning, the reactant, and the end, the product, and I wanted to ask you what got us here. What were the reagents? So if you take a look at reactant to product, I think we can completely see the reactant represented in the product. It's just this extra, attached to this middle carbon right here that I'll dot. We just have 3 extra carbons, right? Well, we know we have a prime candidate here to create an enolate, knowing that we'll fully deprotonate this middle carbon right here. So if we actually just toss in as a first step, the corresponding, component right here that makes up our ester, if we just have the conjugate acid and base, will certainly deprotonate this position right here, making it a good nucleophile. And it doesn't even need to be complicated. Let's just make this an SN2 reaction. You could have propyl chloride, propyl iodide, propyl bromide, like I've shown here. Anything that has a good leaving group that has 3 carbons attached, just plain old SN2. Okay, moving on, middle problem. So again, what we have here is, an ester. And as a first step, I gave you potassium tert butoxide. Good base, good bulky base. All that's going to do for us is create an ester enolate. Yeah, there we go. I drew it weird. So we're going to be attacking from this carbon right here, right? Just put a lone pair right here. So then what's next? What's this next step? Well, yes, that's right. Another blast from the past. I threw in an enone. Now remember, with these enones, we have resonance such that this position right here, when we talk about a 1,4 system right here, it's this 4 carbon right here. We're gonna do a 1,4 addition here, such that, we know this, because of this resonance, we have a partial positive kind of character at this carbon, and soft nucleophiles do 1,4 additions. Now remember, soft versus hard, one of the things that we can identify soft nucleophiles with is if the charge is delocalized among a network of atoms in a nucleophile. And that's the case with our ester enolate. They are soft nucleophiles. So we will do a 1,4 addition here. So the arrows will look something like this. I'll even erase this, but we're gonna basically redraw them. We have attack over here. This bounces over, this bounces up. Eventually, you'll end up with a product that looks like this. I'm gonna flip this methyl group down. This is the carbon. I'll dot this one, and I'll asterisk this one. Dot carbon bonds to asterisk carbon. The asterisk carbon has a methyl group. I'll draw that up, which is why I see it up over here. And then we've 1, 2, 3 more carbons. 1, 2, 3, and it's 1, 2 carbons away from the asterisk that we have this. So at first we have this kind of looking thing, but we know with this type of reaction, the enolate flips back over to a carbonyl. And you might remember, this is actually called a Michael addition, because we end up with that very characteristic 1,5 dicarbonyl relationship. So yes, this stuff doesn't go away. Cool, Michael addition with an ester enolate being a soft nucleophile. We've got the 1,5 dicarbonyl. And last but not least, what we actually have down here, you can see what looks to be a Claisen product, right? But yes, we are putting this ish in reverse because we're pumping back in the very stuff that helped us get there. And what we're actually doing is a retro Claisen. We're going to be taking this Claisen product and reverting it back to the very stuff that got us there. Now, the one thing you need to kind of decide is you need to identify which piece still has the ester character. We see that's this side over here. Once you've figured that out, you can basically go to the alpha carbon and know that that alpha carbon belongs to this side. So then you can draw a squiggly line and say anything to the left was was the one that got attacked and it lost, the leaving group. So when you come back over here, we can basically just say this is one whole piece, which is why you see it drawn over here. And then you kind of redraw the left, whatever part isn't represented. And then you give it the very group that will come in and do the initial attack to start the retro Claisen process. Okay, gang, that does it for problem 2. We have 3 and 4. We have a mechanism and a synthesis problem, so stick with me, and I'll see you in a second. Okay, gang, in problem number 3, we have to draw the mechanism, and I'm sorry for asking for you to do it, but I promise it's good for you. Drawing this Melonic ester synthesis reaction, the mechanism. So if you can see, what I've already done is I've drawn the whole thing out. This reaction, as I'm sure you've probably picked up on, I personally don't think it's crazy difficult, but the part that can be difficult is all of the small acid-base reactions that help you transform certain steps to get prepared to actually do the new knowledge that we've gained, like the decarboxylations and like the ester enolate attack and all that stuff. So let's just step through this. In step 1 of our reagents, we obviously have sodium, ethoxide, and ethanol, and with this diester, all we're doing is deprotonating that sweet, sweet alpha carbon wedged in between our 2 ester carbonyl carbons, right? So I obviously am at a premium for board space, so I made sure I brought in ethoxide, I deprotonated that carbon, and I didn't do like the ester enolate thing, like I didn't draw it in that form. So, but if you did, that's totally fine. Lone pair right there. Then we usher in our benzyl bromide, right? So we went ahead and we attacked that beautiful benzylic carbon, kicked off bromine, a little SN2 reaction. So when we move over here, we see that we have this carbon right here attached right here to this carbon, which I'll asterisk right over here. So nothing so crazy so far. We move into our third step. Right now we have our, another round of ethoxide and ethanol, and we have one more proton on that middle, alpha carbon. We deprotonate it. And sorry, the arrows are a bit wonky, but this is just showing this asterisk carbon getting deprotonated one more time. So you see a lone pair over here. And then, oh, I'm so sorry. I forgot to, I'm missing a step. Yep, step 4. So we go ahead and attack this position, kick it off. And then you can see at that point, we kind of have, just if we ignore this for a second, we just have this structure, right? Just like we started with, but we have the 2 groups here and here attached at that alpha carbon right here. And then we have the very long process of step 5, which ultimately results in a decarboxylation, but a lot has to happen first. We actually are going to transform both of these esters back into carboxylic acids, and in my opinion, that's the most annoying part of this problem. So what you're going to see a whole lot of here is many steps smushed into one, just because I can't write all of them out and on the board at one time. So because we are going to attack with water at some point, and because these are not really strong electrophiles, we're going to do our carbonyl, activate the carbonyl step. We're going to protonate our carbonyl oxygens with acid. You can see they're both protonated plus charges. That makes our carbonyl carbons more susceptible to nucleophilic attack for nucleophiles that aren't super great. That in this case being water. Water comes in both scenarios, and we're going to attack the carbonyl carbon. Yes, that's right. We're going to be doing an addition elimination. Kick electrons up on both of the carbonyl oxygens. We have our tetrahedral intermediates. I kind of cheated here. We want these ethoxide groups to leave because we want to kind of go to a carboxylic acid form. You could separately deprotonate this because we want it to stay and then protonate this, but I did an intramolecular acid-base reaction because realistically, these are super close. They could just swap protons very easily. So I showed this oxygen grabbing this proton and dumping electrons back onto that oxygen. Same thing over here. Then back over here, we have our, ethanol, our OET piece that's protonated, positive, now in a better state to be leaving groups. So what I showed here is electrons swinging down. We reform a carbonyl in both situations. And then this is the elimination part of our addition elimination reaction. I'm driving off ethanol in both situations. So now we're here. We're almost ready, almost carboxylic acids, but I had one more step where we deprotonated both of these suckers. And now finally, if you see right here, now we're in carboxylic acid territory. But I think you realized I actually redrew this one to look like this. You don't have to do it, but the arrows look a little prettier when you do it because now we can finally do our decarboxylation. All right, decarbox. Now, what happens, remember, one carboxylic acid reaches out, the oxygen here grabs the hydrogen of one of the other carboxylic acid. That frees up these electrons right here to swing down and form another double bond here, which creates your CO2. And then we finally sever this from the structure by showing this arrow swinging over, right? And that helps with the fact that this carbon loses a bond when this oxygen takes control to grab that proton. CO2 leaves, which is right here. And what you can see over here is now we kind of have like a dienol, right? We almost have two, we have two OHs in a double bond. One of those will flip back to being in the keto form. So I showed it. You can show this different ways. There's no like one correct way. I would just mirror what your professor does. Some people will show this double bond. They'll show like an intramolecular step here, but what you can definitely do, electrons swing down, this carbon grabs a proton from hydronium, and then what we can also have, after the fact is we have a protonated carbonyl oxygen, water cleans up, you get your product. Okay, gang, long mechanism. Hopefully, if you had any confusion, this cleared it up. We have one more problem, a synthesis. Let's finish strong. Okay, gang, to wrap up this walkthrough, we're looking at this wonderful synthesis problem. And yes, I did throw it up here, but I think this one is, when I looked at this one for the very first time, I did not complete it. It's a toughie. So if we take a look right here, what we have is we have ethanol, and then we have 2-pentanone, and we need to, using ethanol as our only carbon source, synthesize that from what we got over here. Now here's the big challenge with this problem. Here at jOeCHEM, we always count our carbons. We are working with units of 2, but this over here is a unit of 5. And that is inherently the challenge we have to work with. Typically, when we have problems like that, historically, we've used like ozonolysis to cleave a bond, to fracture something, to get units that can add up to what we need. However, what I love about this problem is that it forces you to kind of think about how you can remove, not only build up to a certain number, but then chop down to meet maybe a carbon count that you're looking for. For example, right, we're just gonna kind of look at this and digest it. Having 5 carbons over here, the really tough thing is like, since we're working with units of 2, we have all these wonderful reactions like the Claisen condensation, we can use Ester Enolates to do SN2, we can build up our carbon count. But maybe follow me here, without doing the work right away, we know we can kind of go 2 plus 2 plus 2 get to 6. But we did learn about decarboxylation this unit, and that is a way for us to subtract 1 to get to 5. So as a very first step in this reaction, and you can see on the solutions I went to here, but maybe more appropriately, think about if we kind of had a 1,3-dicarbonyl situation, something like this. Decarboxylation would help us eliminate this carbon, and in this structure we have 1, 2, 3, 4, 5, 6 carbons. But we know when we get rid of CO2 to, in the air, to the atmosphere, we could go back down to 5, and that's the crux of this problem. So if we have hydronium and heat, right? If we step this back one, I think it makes sense to think that we have, 5 to, keep the skeleton of 5 right here. And then it's right here at this carbon, because we kind of want to build in the center. That'll help us kind of figure out how we can we wouldn't want to kind of add this onto the end over here. If we add over here, what you can see is we'll have this kind of this ester piece down here. So, and you can see, I'll keep the carbonyl that I had over here, but then this OH will be just a piece of 2, right? It'll kind of, you can see we can add this on with ethanol right over here. So I almost want you to think that we had something along the lines of this. Because when you look at this, we have 1, 2, 3, 4, 5, 6 carbons. That makes sense to us. So that's what we have right here. And I know that's not what we have right here, but to get these kind of extra 2 carbons over here, right, if we step this back, right, we could deprotonate this position and then just add 2 carbons through SN2, right? And I know this is ethyl bromide and we can only work with ethanol, but we could easily do a PBr3 and SN2 replacement of the OH with a bromine. So we walk back to the decarboxylation. We know we're going to pass through this carboxylic acid, but we can replace that with an ethyl piece. We can, maybe this better explanation. We see we have 1, 2, 3, 4, 5, 6, 7, 8. We need to eventually build this up through a Claisen condensation. So let's just get back to, something that looks like this, but we see this ethyl group right here that we kind of see over here. So stepping that back, right, we can deprotonate this position, and then through SN2 add this. So that's how we kind of go from here back to here. And once we've gone to here, now it's really just building this up through Claisen stuff. So if we back this up one step, we actually, add in ethoxide and ethanol, right? We can deprotonate this. I won't show that though. We could, using itself, right, do a Claisen. So that means this carbon would bond to here. We kick this off. That's how we get 1, 2, 3, 4, 5, 6 attached here and here. That would be that'd be right here and right here. Now we're up to 1, 2, 3, 4 carbons. We can step this back with just, we just have a regular old ester. So since it's 4 carbons, let's just do, Fischer esterification. Acid step 1 back, H+. We have acetic acid and ethanol. They'll smush together. We'll chop this off and smush this together. And then when we need to make acetic acid, we can just oxidize this up. Spend some time with this one, gang. This is a hard synthesis problem. It's not very long, but it's in my opinion, sometimes it's not the long ones that are the hard ones. It's the ones where you need to be really clever at very particular steps. And if you can't see that one part through, it's almost impossible to get to the end. So spend some time with this one. Don't feel bad. It's a hard one for sure. But gang, long walkthrough. Thank you for making it to the end and being a jOeChemist. I really appreciate you watching. I really hope the website has been helpful. If you haven't subscribed yet on YouTube, give that subscribe button a click. And I hope to see you all in the next video.